As I mentioned before, what I'm going to do is kind of finish up the nomenclature information that we talked about the other day. I did that with the other half of the class last time. I also posted the lecture up there on your side there in terms of Canvas, but I wanted to officially go over it with you guys as well, as in addition to just me, obviously, or just them. So just to refresh where we're at, all together, we were talking about type 1 and type 2 compounds. Just move a couple things out of my way here. There we go. So type 1 and type 2 compounds, if you remember, are essentially ionic compounds. So we have type 1 compound, which is between a metal and a non-metal. And as we talked about today and last time, this is going to allow that transfer of electrons, and this is going to create an ionic bond or ionic compound. And the important part always when you're dealing with metal and non-metal is really the location or where the metal comes from. In the case of type 1, the metal basically is from group 1, group 2 on the periodic table, group 3 are zinc, cadmium, or silver. And really what all those guys basically have in common is the metal has a fixed positive charge. And if you remember, everybody in group 1 has a +1 charge, everybody in group 2 has a +2 charge, everybody in group 3 has a +3 charge, zinc has a +2 charge, cadmium has a +2 charge, and silver has a +1 charge always. Again, even though they're transition metals, they basically can have that type of fixed charge. And when we name these guys, again, pretty straightforward. We use the whole name of the metal. And remember that our non-metal pretty much gets the IDE treatment at the end. So something like sodium chloride, for example, NaCl. Na is group 1, which means the cation is Na plus, Cl minus. Because of that Na plus, we know the whole name of the metal, and the non-metal there getting the IDE name at the end of it. Also, again, if we had something like CaCl2, here again, looking at calcium and Cl, calcium being a metal, Cl being a non-metal, calcium is group 2, which is why there's a +2 charge. Cl is group 6, which is group 7, which is a -1 charge. And again, it is the metal that's the most important. We would use the whole name. And again, we would use chloride. Even if there's 2, it has absolutely no effect on the name. You should not use any type of prefix here or anything like that. Now, we also talked about type 2 compounds. And that's sort of, I think, kind of where we left off when we were here together with everybody. Type 2 is also a metal and a non-metal, and also going to be an ionic compound, also going to have that transfer of electrons is going to occur, and also the metal is the most important one in that sort of arrangement. The metal will be a transition metal other than silver, cadmium, or zinc, and it will be just to the right of the transition metals underneath the staircase. So, for example, something like if you look over there, lead, bismuth, tin, antimony, these guys which are underneath the staircase and are metals have a variety of charges. And what the difference is here is the metal does not have a fixed charge. It has a variable charge, which means in certain cases it may be like +2, other cases it may be like +1 and so forth. So that is the main difference. Always metal, non-metal. You should always concern yourself with the metal and where it's located. The good news is it's pretty much named the same way. We use the whole name of the metal. We use the non-metal and drop the last part there and put that IDE at the end of it. And the difference, though, between the two is we use a Roman numeral. And what does the Roman numeral indicate? Well, if we look at FeCl2, Fe is iron. That is a transition metal, which automatically should tell you, I have no idea maybe what the charge is, but you will always know what it's bound to. So Cl is group 7, which means it has a -1 charge, and there are 2 of them. And basically what that means is that's a grand total of -2. The iron here has to be +2 to balance it out. So we would call this iron Roman numeral 2. Again, not how many metals you have, but what the positive charge is if you took just one of those metals out and figured out, again, that positive charge. Same thing as we did on the other side. Even though there's multiple Cl's there, has no effect on the name. And this would be iron 2 chloride in this particular case. Any questions on that there? Okay. So I think that's sort of where we were. Here are some of these sort of transition metals. Again, cobalt could be +2, +3. Copper can be +1, +2. Again, we use the Roman numerals. There is an older way of naming things. Like, for example, iron would be ferric or ferrous, kind of the old school way of naming it. Ferric would represent iron with a +3 charge. Ferrous would represent iron with a +2 charge. The IC has the larger positive charge. We really don't use it very much at all in this sort of class, so you don't have to worry about that. You may see it in the book, but most people don't really use that older way of naming. So if it is a type 2 type of situation, you should always use Roman numerals here. One that's kind of weird in terms of that is mercury. Mercury like this and mercury like this. Oddly, the mercury that has all the 2s is actually mercury 1. And the mercury that has just the 1 2 is the mercury 2 ion. And that's because really the first one is 2 +1s together. So that's why that is sort of like that. How do you know the difference between the sort of the 2 of them is the mercury one will have that extra 2 on the bottom when you look at the formula. So if you got kind of like that extra 2, in most cases is going to be the mercury 1 ion. So that's kind of a weird one to keep in mind. Again, you can see some of these guys that are outside the transition metal regions also again have a variable charge, and they're treated as type 2 compounds in this particular case when we're naming. So we sort of just touched upon this, but just to reiterate, when we are dealing with type 2, again, it's going to be that metal that kind of helps us determine that it is a type 2 compound. We want to always look at the metal, find a location, and then we would figure out the charge on the metal. And again, we would do that from the non-metal it's attached to and kind of work our way backwards. Again, no prefixes here, just Roman numerals with these guys. So why don't you maybe try some here and see what you come up with. So I think you have that guy, you have this guy, you have this guy. And while we're at it, let's give you some names and see if you could write the proper formulas. Let's go with iron 2. Let's go with iron 2 phosphide. Let's do copper 1 oxide. And let's do nickel 4 chloride. All right, so take a minute or two. Guys on the left, let's go with proper name. Ones on the right, let's go with proper formula. A reminder as well, as we talked about, whenever you put an ionic compound together, you want to make sure all the positive charges balance out all the negative charges. So make sure that all balances out. Take a minute or two. That is chlorine, which is a non-metal. So right off the bat, you should know you're dealing with an ionic compound because you have a metal and a non-metal together. Always in this situation, it is the metal that's really important. And in this case, the metal is cobalt, which is almost dead center there on the periodic table, number 27. That also tells you that that is a transition metal, which means we're dealing with type 2 here in this case. And what that means is we're not really sure what the charge might be on the cobalt, but we do know the Cl is group number 3, and there happens to be 3 of them. So if we just draw them out, that's a grand total of -3, which means the cobalt in this case should have a positive 3 charge to balance it out. Then we use the whole name of our metal, which is cobalt. We do need the Roman numeral to indicate in this particular case, we're dealing with the cobalt with a +3 charge. And again, even though there's multiple Cls, when you're dealing with a metal and non-metal, has no effect on the name, and it would be chloride in this case. So this would be cobalt, Roman numeral 3, chloride. Any questions on where I got the name from? Okay. Then looking at our next one, again, same sort of analyzation. Cu is a metal, I is a non-metal, again, ionic. Again, looking at the metal, which is copper, also found right there in the transition metal region, 29, tells me this is type 2, which means I need to figure out what is the charge on the copper. The good news is, as I mentioned, you will know what the charge is on the I. I is group number 7, which means it has a -1 charge. So remember, always positive, negative guys need a balance. So to get us to 0 in the simplest way, the copper here would have to be +1. That means whole name of the metal, which is copper, Roman numeral for the charge on the individual copper, which is 1, and iodine becomes iodide, IDE at the end of it, copper 1 iodide. Question on that particular one there. Now, looking over here at SnBr, Sn is tin, which is a metal. Br is a non-metal, so again, metal, non-metal situation, ionic. The metal here, which is tin, is not a transition metal, but it is one of those guys to the right underneath the staircase that also behaves like a type 2 compound. So same approach here, not sure what the charge is on the tin, but I do have Br, which is group 7, and there happens to be 4 of them in this case. So if you just draw them all out, that is -4. To balance that out, that would be +4. And that means that this is tin, Roman numeral 4. Again, not how many tins we have, but the actual positive charge that's happening there. And same deal, because this is metal, non-metal, even though there's 4 BRs, has absolutely no effect on the name, should not be using a prefix. And this would be tin, Roman numeral 4, bromide. Any questions on any of those 3 there? Okay, so if we have names and we want to do formulas, we need to go backwards here. So the nice thing is we just want the basic units that make these things up. So when I see iron Roman numeral 2, that automatically tells me I have an iron with a +2 charge. That would be my cation. Yeah. Phosphide, IDE means it's negative. Phosphorus is where that comes from. Phosphorus on the periodic table is group number 5, which means it has a -3 charge, and that would be my anion. So when we put our cation and anion together, positive and negative, we want to make sure that we end up with no charge. So common number between +2 and -3 is 6. In order to get my iron to 6, I need not 2 of them, but I need a grand total of 3 of them. To get the phosphorus to 6, I need 2 of them. And we end up with a formula that looks like this, Fe3P2. Any questions on that one there? Same thing here, copper Roman numeral 1. As soon as I see that Roman numeral, I know it's type 2. I also know the charge on my cation is +1. Oxide, IDE is negative. Ox is oxygen from the periodic table, which is group number 6, and a -2 charge, which is our anion. Here, putting these guys together, simplest way to get to 0 is I need one more copper with a +1 charge. That means it would be Cu2. Oh, one oxygen, 2 coppers, each at +1. Any question on that particular one? Lastly here, nickel 4, again, type 2 because of the Roman numeral, also means my nickel has a +4 charge. Chloride is chlorine with a negative charge, which is group number 7. So it's got a -1 charge. Again, when we put this together, we need more negatives. That gives me -2. That gives me -3. And 4 of them gets me to -4 to balance out the +4 that's there. And this would look something like that. Any questions on how to go from name back to formula or formula back to name? So these are type 2 compounds. Again, Roman numeral used here. Roman numeral, again, not how many you have, but the actual positive charge that there is on the actual metal. All right. So a couple of things like we sort of touched upon earlier here. Again, type 1 guys, which is group 1, 2, and 3, are again our zinc, cadmium, our silver, which again, these guys typically +2, and silver +1, all have fixed charges. All these guys are going to be type 1 compounds. No need for Roman numeral. Our transition metals and those guys to the right going to have that variable charge and do need a Roman numeral when we do type 2. All right. So you got another example here just to make sure. Whoa, that's really small. So I think you have on your paper MgBr2. You also have Li2O, and you have CrF2. Take a minute or two here and come up with the proper names. Okay, so let's take a look. So same approach. I see Mg, which is magnesium. That's a metal. I see Br, which is a non-metal. So again, automatically tells me ionic we're dealing with here. Again, always in this situation, we want to look at the metal. So here we see magnesium's actually group number 2, which means that this is type 1. And that means that the magnesium has a fixed charge of +2 because it's group number 2. That also means that we don't have to worry about Roman numerals or anything. We just use the whole name of the metal, which would be magnesium. And again, even though there's more than one Br, it just becomes magnesium bromide. The cation formula would be magnesium with a +2. The anion formula would be Br minus. And again, that's why there is 2 of these to balance out the charge. Any questions on that one? Looking at the next one, we have Li, which is lithium, which is a metal. We have O, which is oxygen, which is a non-metal. So again, ringing up ionic for us. Looking at our Li, that is going to be lithium, which is group number 1, which means it has a fixed charge of +1. Oxygen is a -2, but it really is the lithium that's most important because, again, that's going to tell us it is type 1 in this case. And because it's type 1, again, don't have to worry about anything other than using the whole name for the metal. And remember, our non-metal, drop the last part and we get the IDE at the end of it, and we get lithium oxide in this particular case. Any questions on that one? Now, same approach here. Cr is a metal, F is a non-metal, and again, going to be ionic. Here, though, the chromium is, again, pretty center on the periodic table, number 24. So that is a transition metal, which tells us it could have multiple types of charge and tells us it is type 2. And I should be doing some Roman numeraling here. So let's think about what Roman numeral I should do. I'm not sure what the chromium is, but I do know fluorine is -1 since it's group 7. And there are 2 of them, which gives me a grand total of -2. So in this particular case, the chromium should be +2. And that means that we would have chromium Roman numeral 2, again, because of the charge. And even though we do have multiple F minuses, it would just be fluoride in this case. So chromium, Roman numeral 2 fluoride, chromium with a +2 would be our cation, and our anion would be F minus. Any questions on any of those ionic namings or what to do with it? Always metal is the really most important one there. Either you'll need to use a prefix, or not prefix, I'm sorry. Either you'll need to use a Roman numeral or you won't need to use a Roman numeral. Any questions on ionic naming? All right, speaking of prefixes, again, very common. People want to use prefixes everywhere they can. So now we're going to actually talk about the proper place for you to use prefixes. This, again, is sort of a decision tree. If it's type 1 because of the metal, just whole name of the metal, IDE for the non-metal. If it is a type 2, you need to determine the charge and use a Roman numeral. So it's actually here with type 3 compounds that we actually do use prefixes. So type 3 compounds, these are covalent compounds. So as we talked about, covalent compounds, pretty much 2 nonmetals together, and pretty much we are sharing electrons here. So this is actually the place to use prefixes and the only place to use prefixes. So when we're doing these guys, there's a few different rules. Again, like I said, it's just nonmetals. We do the first element first, and we use the whole name. And then we do the second element as it was a nonmetal with the IDE. We don't really have that table here. We have a similar one, but it's not 5.3. So whole name of the first one with the appropriate prefix, whole name of the second one with the IDE at the end of it with a prefix. Prefixes like mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, and so forth. There's a couple of rules. We do not use mono on the first name, but you can use it on the second name, so that's all good. And the other very common thing that occurs is sometimes we will get a prefix and the first letter of the element. We'll get a couple of vowels together. So for example, if we have something like CO, C is carbon, nonmetal, O is oxygen, nonmetal. We would not use mono on the first name, so we would just use the whole name of the first element. The second guy, we can use mono, and we make IDE out of it. Now, if we just wrote it exactly the way it is, we end up with carbon monoxide, and we really don't call it that. So because there's two O's, we typically will drop the O off of the first guy, the prefix, and this actually is called carbon monoxide. Again, one O. So it's a very common sort of thing. If you get a couple of O's that back up to each other, O off the prefix gets lost. You get like an A and an O. We get rid of the A. Two I's is actually okay, actually. But an O and an O or an A and an O, we typically get rid of the vowel off of the prefix. The nice thing about these guys is they are probably the easiest, but they are also the one people screw up the most because they want to do all kinds of weird things. So the good news is here, you don't have to worry about charges with these guys. You just got to pick the right prefix. So here's through 8. 9 is nona. 10 is deca. And again, sometimes we do drop sort of that vowel out of the way off of our prefix so that we don't end up with, kind of a weird, awkward sort of spelling for a particular name. Again, the only really rule is, other than that, is no mono on that first one, but absolutely can use it on the second one, or the second name. The second name, obviously, as we saw there, gets the IDE at the end of it. And here's what we were talking about. Again, tetraoxide, again, the A and the O backing up to each other. We typically get rid of the A, and the two O's, like we just talked about, we get rid of the O, again, just to make it a little bit better. We talked about some things that have common names. Again, H2O is water. It is not dihydrogen monoxide. NH3 is ammonia. And the other one that we had on that list was CH4, which is methane. And again, that is the simplest sort of organic molecule you could have. One thing that is a little bit different is when we do have something with hydrogen, like HCl in the gas phase. HCl here would be called hydrogen chloride. If you had like HBr, this would be hydrogen bromide. And it's because hydrogen is a little bit different. Even if we had something like H2S, this would still be known as hydrogen sulfide. And that's because although they are both nonmetals, it is hydrogen. Hydrogen's got some unusual properties. We kind of think of hydrogen almost as H plus and Cl minus. So almost like an ionic compound in terms of naming, even though they're really sharing electrons. So hydrogen's a little bit different. And that's why we have two H pluses over here with our S2 minus, again, to balance it out. So other than hydrogen with something in front, pretty much all nonmetals will be named with these prefixes here. So why don't we try some here just to see what's going on. So I think you have I2O7, you got CO2, you got PCl3, and why don't you write the formulas for, let's go with, carbon tetrabromide. Let's go with dinitrogen pentasulfide. Let's go with triphosphorus. What am I doing there? Triphosphorus dioxide. Just make things up here. Why not? All right. So one's on the left here, proper name. Guys on the right, proper formulas. So take a couple of minutes here and see what you come up. Think about it or overthink it. It should go pretty quick, especially these type 3. But they are the ones that people kind of mess up the most on. So when I look at this, I see I, which is iodine. That's a nonmetal. I see O, which is a nonmetal. So that's two nonmetals. That tells me we are type 3 situation, which is covalent, guys. Also should be really happy because we don't have to worry about balancing charges or anything like that. All we essentially have to do is pick the right prefix. So the prefix for 2 is di, and we use the whole name of the first element, which is iodine. Prefix for 7 is hepta, and the next guy would be IDE for the oxygen. So this would be heptoxide. Again, here it is hepta, and then we have the oxide, again, that AO situation happening. So we'll get rid of the A there. So diiodine heptoxide here would be our correct name. Coming down here, I see carbon, which is a nonmetal. I see oxygen, which is a nonmetal. Again, should indicate to you that it is type 3, which means simply we just need to write what's there. Only one carbon means mono for the prefix, but we do not use that on the first name. So we just use the whole name of the first guy, which is carbon. Prefix for 2 is di. And again, the second guy gets the IDE treatment at the end of it. So this would be carbon dioxide. Any question on that particular one there? Okay. Looking over here at the third one, we have P, which is phosphorus, nonmetal, Cl, which is a nonmetal. Again, 2 nonmetals tells us we're doing type 3. Whole name of the first one, since there's only one and we don't use that prefix, so that's going to be phosphorus. Prefix for the second guy there is tri for 3, and chlorine again gets the IDE treatment, phosphorus trichloride. Any question on any of those 3 names, where any of the parts came from? Okay. Now I think almost the super easiest out of all of them is when we have the name to go to formula here. When I read carbon tetrabromide, soon as I see that prefix, I should be really happy because don't have to figure out anything in terms of charges or balancing. Simply just need to write what's there. Carbon with no prefix on the first name means I just have one. Tetra is the prefix for 4. Bromide is Br. 4. So CBr4. Same thing here on the next one. I see di and I see penta. Those are 2 prefixes. Di is 2, penta is 5. So don't have to worry about balancing anything. So N2 for the di and S5 for the penta here. And that would be our formula. And lastly here, tri and di, same deal. Tri is 3. Di is 2. Prefix means don't have to worry about anything other than writing what is there. Oxide is oxygen, and we end up with something like this. Question on type 3 compounds here. Again, they are the simplest, but they are the ones that people really screw up the most. They try to do all kinds of weird balancing things. You could clearly see here there is no use of Roman numerals. There is only prefixes here. So to reiterate, type 1, no prefix, no Roman numeral. Type 2, you need a Roman numeral, no prefix. Type 3, which is what we're talking about here, prefix, no Roman numeral. Yeah. So if you find yourself writing something like copper, Roman numeral 2, dioxide, it is definitely going to be wrong. So these 2 things should never really be in the same name. They're each obviously used for specific situations. Any questions on that there? Okay. So just to review what we just talked about, type 1, ionic compound, no sharing of electrons, transfer of electrons. Metal has a fixed charge, so no Roman numeral needed. Type 2, metal, nonmetal, ionic compound. Metal has a variable charge, which is why we do use Roman numerals. to tell us what charge it is. And type 3, non-metal sharing of electrons, prefixes only. Any questions on any of those guys there? Here's sort of a decision tree based on sort of stuff we talked about and which way to go and what to sort of use. All right, so the last thing we're going to talk about in terms of naming is polyatomic ions. An example of that is NH4NO3. So NH4NO3 is actually two different polyatomic ions that are together. We actually break it apart right there. We end up with a nitrogen and 4 oxygens. And those guys move around as one unit altogether. And that overall unit has a +1 charge. And this is what is known as the ammonium ion. Over here, that NO3 is NO3 minus, that 1 nitrogen and 3 oxygens, all stay together and has a -1 charge. And this is what is known as the nitrate ion. We actually just drew this guy not too long ago. And again, the nitrogen and the hydrogens, they are all sharing electrons here. This is all covalent, but it is an ion because overall it does have a +1 charge. And same thing with our nitrate. It actually looks like this if we draw the Lewis structure. Those oxygens and the nitrogens are sharing electrons, and the overall guy has a -1 charge. This is essentially our cation, which is positively charged. This is our anion, which is negatively charged. And the reason why when we put it together such as this, just like anything else that is positively charged and negatively charged, we want to make sure that we get an overall charge of 0. So this whole thing has a +1 charge. This whole thing has a -1 charge. So actually, when we stick it together, we just need one of each. This nitrogen and 4 hydrogens will move around as one unit. It will never break apart into individual hydrogens and nitrogens. Same thing on the right-hand side, that nitrogen and 3 oxygens will move around as one unit and never break apart. How do we name these guys? Well, in this case, we actually just use the names of the polyatomic ions. This would be known as ammonium nitrate when we put it together. For the most part, the ammonium is the only positive polyatomic ion you'll come across. Most other polyatomic ions are usually negatively charged. So a good majority of our polyatomic ions are negatively charged, which means what we usually end up with is we usually end up with a metal and a polyatomic ion. And basically, the polyatomic ion is negatively charged. The metal is positively charged. And what that means is whenever we got that metal involved, it's always the most important thing. So just like we did when a metal and a non-metal is together, if the metal is group 1, group 2, group 3, if it's zinc, cadmium, or silver, it is basically named just like we do a type 1 metal, which means we don't use a Roman numeral. We just use the whole name of the metal. And we use the whole name of the polyatomic ion. Even if there's more than one, we use the whole name of the polyatomic ion. If that metal there is a transition metal, or lead, tin, those guys, it will be a type 2 metal. And we name it the same way, which means we need a Roman numeral. We do the exact same things we did before. We use the whole name of the metal. We use a Roman numeral. To indicate the charge on the metal, and then we use the whole name of the polyatomic ion. So a lot of times when we're dealing with polyatomic ions, we're going to be dealing with metals with them, and we pretty much name it the exact same way as we name type 1 and type 2 compounds. So it kind of works out the same in a lot of cases because of that. So where are these polyatomic ions? Where there is a table, and here's a table, I believe, from your book. And there's a lot of polyatomic ions. You do need to know the names and the formulas and the charges so that you could put everything together correctly. So there is a way that you could kind of group things together to sort of help you out in terms of the names is, for example, if we look at NO3 minus and NO2 minus. So the guy with 1 nitrogen, 3 oxygens has a -1 charge. That guy is known as nitrate. The 1 nitrogen and 2 oxygens that have a -1 charge, that is known as nitrite, ITE. If you look at something like SO4 2 minus, 1 sulfur and 4 oxygens has a -2 charge. That is what is known as sulfate. SO3 2 minus, 1 sulfur, 3 oxygens with a -2 charge. That is what is known as sulfite. So there are guys that are related to each other in like a group of 2. The only difference between the NO3 minus and the NO2 minus is the number of oxygens. The one with the most oxygens usually will end in 8. You can remember it like you ate too much. That's the most oxygens. The one with the least number of oxygens ends in ite. So sometimes people will remember all the 8s and know that the ites are 1 oxygen less. The charge is exactly the same. Or vice versa, you can memorize all the ites and know that the 8s are 1 oxygen more. There are groups that are like 4 things related to each other. And this guy right here is the most common one that we see. This is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. They all have a -1 charge. The only difference is one has 1 oxygen, 2 oxygens, 3 oxygens, 4 oxygens. If we break this group up right about here, and we go to the right, those are guys with the least number of oxygens. So this would be chlorite, ITE. This guy would be chlorite as well. But you cannot have obviously the same name for 2 different things. So when we have a group of 4 that are related to each other, the one with the least number of oxygens will start with hypo, or kind of scribbled it there. So that is hypochlorite. If we look at the guys on the left-hand side, they have the most oxygen, so that would be chlorate. This guy would be chlorate as well. But again, we cannot have the same name, so the one with the most becomes perchlorate. So that's how we get to perchlorate. Most oxygen starts with per, ends with 8. Second most oxygens just ends with 8. Least number of oxygens, or second to least number of oxygens, ends in ite. Least number of oxygens altogether starts with hypo, ends with ite. By the way, this is Cl. It means you could substitute it out for somebody else, like BrO3 minus. Instead of it being chlorate, this would then be bromate. So it's kind of named the same way. In addition, you at most part you'll probably be responsible for sort of this chart that's in your book for sure, and on the review sheet it'll tell you specifically which ones you should know. But for the most part, what's on here you probably should kind of know. And again, the name and the formula and the charge is really important, so you can balance out everything correctly. So, and again, I believe this is the chart from your book, if I'm not mistaken. There are a couple of other things that we will see when we look at sort of these polyatomic ions. For example, if we take carbonate, which is CO3 2 minus, and if we put an H plus, not just an H, but an H plus in front of it, we end up with HCO3 minus. This is what is known as hydrogen carbonate. And that is also sometimes referred to as bicarbonate. So they sometimes use that bi instead of hydrogen as well. You also see that with bisulfate here. instead of hydrogen sulfate. So that bi is sometimes used. A vast majority of these guys will end in 8 or ite, but there are some polyatomic ions that actually end in IDE, like OH minus is hydroxide, IDE. CN minus is cyanide, IDE. But a good majority of them will end, like I said, in either 8 or ite. And again, the one kind of positive and only positive sort of polyatomic ion, or one of the few that you'll come across, is NH4 plus, which again is the ammonium ion. Not to be confused with NH3 that has no charge, and that is ammonia. So this is not a polyatomic ion, no charge, but this one is. So those are two that get kind of confused a lot. Any questions on that there? Why don't we just try a few here just to make sure? I'll just kind of flip this so you have something to look at. This is another sort of table similar to the one you have obviously in your book. So why don't you try to name a few here or give you some formulas. So let's go with NaNO3. What is the proper name? Let's go with CaOH2. Let us go with CR. I want to do that. Let's do CrCN4. And then why don't you try to write some formulas for these following names? Let's do magnesium, hydrogen carbonate. Let's do potassium sulfate, and let us do iron 3 nitrite. All right, take a couple of minutes here and see what you come up with, and then we'll double check. Again, since like I said, most of the time we're going to see those polyatomic ions with a metal. We want to see, obviously here we have a metal. Here again, if you could recognize that at some point, hopefully as nitrate, which is our polyatomic ion, we would split it right about here. That means our sodium, which is group 1, has a +1 charge. Our nitrate from the list there actually has a -1 charge. And that's why when we put them together, we just need one of each of those. But like usual, the metal is our most important sort of thing to look at. It is sodium, which is group 1, and type 1, which means we just use the whole name of sodium and we use the whole name of our polyatomic ion. And this would be known as sodium nitrate. Any questions on that particular one there? Same thing here. When we look at the second one, I see Ca, which is calcium. That tells me it is group 2, which has a +2 charge. Again, looking inside the parentheses, I see OH, which tells me it's OH minus. So again, the metal is the most important guy here. That is calcium, which is type 1, which means we just use the entire name of the metal. Then we use the entire name of the polyatomic ion, even though there are 2 of them, has no effect on the name here. This would be hydroxide. Question on that name. Why is there 2 of them there? It's because this is +2. This is -1, which means we need 2 of these guys to balance it out. Also really important is if you look at this formula, we have parentheses there. And that is because if I wrote it like this, CaOH2 with no parentheses, that would imply that I have 1 calcium, 1 oxygen, and 2 hydrogens, which is not the case here, right? I have 2 oxygens and 2 hydrogens. So whenever you have more than 1 polyatomic ion, you do need to put parentheses around it and the number on the bottom to indicate how many you have. So always more than 1 polyatomic ion, got to put those parentheses around it to indicate that you have like 2 of those units, 3 of those units. In the case here, when you just have 1, you don't need the parentheses. Coming this way, I see Cr, which is chromium, which is a metal. I see Cn, which is cyanide right there. And in this case, Cr is a transition metal, which tells me I'm not sure what that is. But just like before, when you learn these polyatomic ions, you will know Cn is Cn minus, and there are 4 of them, which means if you just kind of draw it all out, that is a -4 charge, which means the chromium here has to have a +4 charge. Because this is a type 2 guy, that means we do need a Roman numeral, and that would be chromium Roman numeral 4 for the charge on the chromium. And just because we got 4 of these guys, no effect on the name. We just used the whole name of the polyatomic ion, which is cyanide. Any question on any of those 3 names there? Okay, then let's talk about going the other way. We want to approach it the same way as we've done the others. We want to basically just figure out what are the basic units of each of these things. So when I see magnesium, I know magnesium is group number 2, which means magnesium has a +2 charge. Hydrogen carbonate is the same as bicarbonate, and that is this guy right here, and that is HCO3 minus. Again, this entire thing stays together and actually has a -1 charge. So when I put these together, I'm putting together something with a +2 charge and a -1 charge, which means I actually need 1 more of these guys. And that gives me a -2 charge and a +2 charge. Now, putting that together in the formula, that's going to be Mg. And because they have more than 1 polyatomic ion, I put my polyatomic ion in parentheses, and I put the 2 on the bottom. And what that means is that I have 2 of these guys, each at -1, gives me a -2 charge. And I have 1 magnesium at +2. +2 and -2 gives us 0 overall charge. Any questions on that one there? Looking at the last 2 here, potassium again is group 1, which means I got a K+. Sulfate is, I would think it would be on here. It's not on this. Yes, it is right there. Sulfate right there. That is SO4 2-. Again, that entire thing has a -2 charge. When we put this together, we actually need 1 more potassium to balance that out, going to give us K2SO4 as our formula. Again, 2 potassiums, 1 and 2, each at +1 each. 1 sulfate at -2. Everybody bounces out to 0. Looking at our last one here, iron Roman numeral 3 means we have an iron with a +3 charge. That's what the Roman numeral means. Nitrite, ITE, is this guy right here. And that is NO2 minus. So same idea here. We're putting a +3 and a -1 together. And hopefully, as you can see, you need a few more of these guys, or a total of 3, to get us to -3. And what that means is when we put the formula together, 1 iron, again, multiple polyatomic ions, so we need parentheses, and the number on the bottom, again, meaning we have 3 of these nitrites at -1, -2, and -3 to balance out our +3 charge over here with our iron. Any questions on polyatomic ions, how to name them, how to write the formulas? Again, for the most part, they follow along the same lines as our type 1 and type 2 ionic compounds. Again, because for the most part, most of them are negative, which means they will find themselves hooked up with a metal. So kind of falls back to that. If the metal needs a Roman numeral, put it in there. If the metal doesn't need a Roman numeral, don't put it in. And even though, as you can see here, we have sometimes multiple polyatomic ions, no prefixes here. It has no effect on the name. The only time you would use a prefix on a polyatomic ion is if the actual polyatomic ion itself, like this guy, had an actual prefix in the name. Other than that, again, you should not be using prefixes here with these guys, other than that rare occasion where the actual name of it has a prefix in it. Any questions on polyatomic ions or naming in general? I believe that should wrap up the naming part of it. We've talked about this pattern. I'll just kind of put it up here in case you want to look at it. That was our group of 4 relationship. And that was sort of our relationship and what we do with hydrogens. And I believe that was it. Any questions on naming or anything like that? Okay, so we will wrap that up here for today. If you do have any questions still, I'd be more than happy to hang out and answer those for you. If you're good, I'm good. Thank you very much for hanging out. I appreciate it.